Hello everyone, Dr. Chen here. So we're going to go over Newton's first law in this video lecture. Newton's first law says, every body persists in state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. This is a faithful translation from the Latin Newton wrote in his book of Principia. So it's kind of hard to understand if we just read this. So let's break it down and try to understand in more easy to understand language. It says an object moves with constant velocity unless there is a non-zero net force acting on it. So what does that mean? It's actually pretty simple. So it has something to do with net force, whether the net force on the object is zero. Now, Newton's first law is more concerned about the case that the net force on the object is zero. If the net force on the object is zero, then what's going to happen? Two different scenarios. If the object is at rest from the start and the net force is zero, this basically you have object at rest and there's no force acting on it. What is object going to do? It will stay at rest if there's no force, right? This is easy to understand. And what is object going to do if it's already moving, but it's moving at a constant velocity, and there is no force acting on this object? And Newton's first law says if the object is moving at a constant velocity and the net force is zero, then the object is going to maintain constant velocity. So this is basically Newton's first law. So in very simple language, it says net force is zero, give us acceleration zero. This is Newton's first law, also called law of inertia. Let's try to think about this. So initially we have a book on a table moving with velocity v. Now if there is a friction, what's going to happen to the book? The book is going to be stopped moving very quickly, right? Because of the friction. So there is a non-zero net force. So the motion of the book changes. Now this is not going to be happen in reality. Let's say we have a book, we have a table, and there's no friction between the book and the table, and the book starts moving at a velocity v. What's going to happen to the book? The book is going to move on and on forever. And this is something that we cannot experience in our everyday life. In our everyday life, we almost always have friction. And this is why it's so difficult for the entire human race to realize Newton's first law. So Newton is the first person to extract what's going to happen from reality to something that he cannot experience, but he can extrapolate what he observed. So you might ask, what happened before Newton? What happened before Newton is that people think Aristotle is right, and actually he's not. Okay, that's why I said Aristotle's statement is incorrect. And this is something, and I don't want to, or maybe we still need to discuss this. No. So before Newton, people think if you want something to move, keep moving, there has to be a force applied to it. Otherwise, it will stop moving very quickly. So before Newton, people think motion requires force. But this is incorrect. Motion doesn't require force. If there's no force, object already moving will keep doing this motion if there's no force acting on it. Now, this is what we observed. If you want a book to move on the table, keep moving, we have to supply a force, but this is because we have friction. If we don't have friction, you have a book moving on the table, it will keep moving forever. Now, this is hard to think, but now we know if we go to outer space that, and you just throw a book moving in the outer space, you can imagine if there's no force acting on the book, what the book is going to do. They will keep moving straight forward forever, right? So there's no net force. So motion doesn't require force. Motion is motion. And Newton figured out that it requires a force to change the motion, to change an object from at rest to start moving, or change the direction of a moving object, or change the magnitude of the velocity of it. It all requires net force. And Newton kind of figured out acceleration requires force. If force is zero, acceleration is zero, object stay at rest, starting at rest or stay at rest, object start moving at a constant velocity or stay at constant velocity. So this is Newton's first law. Now, it looks easy after we figured out, but as I mentioned, we live in an environment that we always have friction. So it's hard for the ancient people to experience or even to think about what's going to happen if there's no friction resistive force at all, which is something that Newton figured out and is the first step of all the mechanics. Now, we have to distinguish what is inertia and what is mass. Now, because Newton's first law says object at rest or stay at rest, object moving at a constant velocity or stay at a constant velocity when the net force is zero. Now, of course, if you have a non-zero net force, then the motion will change. Now, inertia is a natural tendency of the object to remain at rest or constant velocity along a straight line. So basically, inertia is a measure of how difficult that it is to change the motion of the object. And the unit of mass is kilogram, as we discussed in our first chapter. Okay, now let's try to understand Newton's first law using a few examples. The sailing boat is moving east with constant velocity. The sailing boat is moving to the east, constant velocity. It asks us what's the direction of the net force on it. Okay, maybe you can pause this video, think about this question for like 1 or 2 minutes, and then restart the video. I'll give you the answer. The answer is C, 0. Why? Because the sailing boat is moving at a constant velocity. And the constant velocity means the net force on the sailing boat is 0. Even it's moving to the east. Actually, the sailing boat can move in any direction with constant velocity, and the net force on the sailing boat has to be 0, right? Okay. Now, a Ford Pinto is parked in a parking lot, and there is no net force on this car. Is it right? Maybe you can pause it for like half minute or 1 minute or so, and I will give you the answer after you come back. Okay, welcome back. So the answer should be 0, right? And this car parked, which means it's at rest, right? At rest. If its object is at rest, what's the net force? At rest, the net force is 0. Pretty simple. Okay. Now we have a car parked at rest. Parked, which means it's at rest. The contacting force on the car from the parking lot surface. What's the direction? So we already figured that from the previous example, the net force is 0, right? So what are the forces acting on the car? This car has to have a weight, the gravity force, so pointing down. And net force is 0. So you have to have another force to add up to this force give you 0. So this is contacting force from the surface, which would be our normal force. And these two forces has to add up to 0. So what's the direction of this normal force? Pointing up. Okay. Now, the same car drives down the highway, even on the moon. Of course, it's not realistic, but yeah. Constant velocity. There is no air resistance. Constant velocity. What's the acceleration? Constant velocity, which means velocity doesn't change. So delta V is always 0. Delta V is always 0. And A, acceleration, is delta V over time. But if your delta V is always 0, your A is always 0, right? So acceleration has to always equal to 0 if a car is driving at constant velocity. Now we have the car. There is no air resistance. What is the contact force on the car from the surface? So we do know we still have weight mg pointing down, and all other forces acting on the car is from the surface. And the net force has to be 0. So how can net force be 0? So the net force has to add up to, well, in this direction. You have normal force and you have all the other force, but they have to all add up to this net force from the surface, add up to this weight, and those two forces has to add up to 0 because the car is moving at a constant velocity. So the net force on the car from the surface is vertical because it has to cancel weight. And the only way that it can cancel weight is that pointing up, because weight is exactly pointing down. Okay. Now let's look at this example. If an object is moving, you can conclude there are forces acting on it. If an object is at rest, can you conclude there's no force acting on it? I will see what's the answer to the first one. If the object is moving, can you conclude there are forces acting on it? The answer is no, right? An object can moving at a constant velocity with net force 0, no force at all. If an object is at rest, can you conclude there are no force acting on it? I guess the answer is no either. You can have force, it's just the net force, which means you add up all the force, net force has to be 0. So we can conclude the net force is 0, but we cannot conclude that there's no force at all. Okay. Let's see. Are there no force acting on the object in those cases? A boat comes loose from a satellite orbit the Earth at a constant speed. Okay. Is constant speed? So we have a satellite orbiting the Earth, constant speed, but the orbiting is circular, right? If it is circular, which means it's constant speed, but not necessarily constant velocity because the direction of the motion is changing. Constant velocity means not only the speed doesn't change, the direction of the motion doesn't change too. So for this one, actually, there is a net force, which is understandable. And the force on this boat is just the gravitational force on the boat from the Earth. Now let's look at B. After a gust of wind blew through a tree, an apple fell to the ground. Now, of course, when the apple is falling, there is gravitational force acting on the apple, and we also might have the wind force, which is air resistance, right? Okay. And a man rested by leaning against a tall building. A man rest. He's at a rest. A man is at a rest, leaning against a building. What are the forces acting on the man? We have gravity. We have normal force. And then we have the normal force from the building of the man. At least those are the three forces acting on him. And there might be friction. D. Parachute. A skydiver fell off the ground at constant velocity. Okay, this time, is there any force acting on the diver? Constant velocity, which means net force is 0. But there is mg weight, and we have air resistance from parachute. Net force 0, right? Constant velocity, net force 0, but there is force. So forces are acting on all four scenarios. Correct answer is E. Yeah. So try to understand these two questions again after we go over these cases, and I think it will give us a better understanding how it works. Okay, I promise the next example on Newton's first law. Now, we have an elevator being lifted at a constant speed. There is no air resistance, no friction. Okay. Now, we want to compare what this T, the magnitude of this T on the elevator and the weight of the elevator. So basically we want to ask what's the net force on the elevator. Is it pointing up, pointing down, or 0? So now I also suggest you to pause this video for 2 minutes this time. Try to answer the question, and I will give you the answer after I come back. Okay, now welcome back. Before I give you the answer, I can tell you I usually conduct a survey during when I was giving a face-to-face lecture on Newton's first law. What's the answer to this one? And most of the time, I only get like less than 20 to 30% correct response. So check whether you get it right. The answer should be B. Why? Because elevator is going up at a constant speed, so the elevator is doing constant velocity motion. Constant velocity motion, which means net force is 0, and we have two forces acting on the elevator. they have to exactly cancel each other. So T has the same magnitude as weight. Now you may argue why the elevator is still going up if net force is 0. Okay, because that's Newton's first law. Newton's first law says if the object is doing constant motion, net force is 0, is keep doing constant motion. And then let's go back. And what clouded our mind is that we're thinking that at the beginning the elevator is at rest. The elevator is at rest, and then we need to have it start moving. Now, at rest, you want to change the state of motion from at rest to moving. We need a non-zero force. Yes, at the beginning of the motion, the elevator is at rest. We need to apply a non-zero net force on the elevator, so the elevator will start motion. But as long as the elevator has gained a sufficient constant velocity and keep doing constant velocity, the net force has to be 0. Yeah. So the answer is B, right? Yeah. So if you're still interested in this question, please just send them an email and we can discuss. Thank you very much for your attention. In the next lecture video, we will be discussing Newton's second law.